In this today's video lecture, we will see moment of inertia of a rectangle. See here, this is x-axis and this vertical axis is y-axis, and this rectangle of width b and height h is subjecting to the centroid or origin of this x-axis, and subjected like this h distance, half h distance is upward to the x side and half h distance is downward to the x side. That means boundary conditions are minus h by 2 and h by 2. And this elemental strip consider of a rectangle, whole rectangle, and this small elemental strip of rectangle of height delta y and width b. And in our previous lecture, we see this term, this is x-axis, vertical y-axis, and this delta E is elemental area delta A, and from that delta A to y distance, this small x distance, and from x-axis to delta A distance, this small y distance, and calculation of moment of inertia about x-axis, we multiply this elemental area to the distance between this x-axis to the delta A and square of this distance y square. That means calculation of this moment of inertia about x-axis, consider this delta A and multiply by y square. Why this y take? Because we calculate moment of inertia about this x-axis and distance between this x and delta A is y square, and integrate it for consideration of this whole body. Similarly, Iy, for calculation of Iy, distance between y to delta y is x, that's why here x square. And elemental area is A, and for consideration of this whole body is delta I. Now, similar concept applied for this rectangle, Ix, moment of inertia about x-axis is equal to area of that element, small element. Like this delta A, here small element is this, and area of this small element is delta y into b. So here area of this small element take b into delta y, and we calculate here moment of inertia about x-axis. So between x-axis and to the this small elemental strip, distance is y, that's why here y, and square of this distance is y square, and consideration of this whole rectangle is take this integration and boundary conditions minus h by 2 and h by 2. So here Ix is equal to integration of minus h by 2, h by 2, and area of that small rectangular elemental strip is b into delta y, and multiply by distance between x-axis to this elemental strip is y square, square of it distance. Write this integration mathematically, minus h by 2, h by 2, this b into this y square is here inside, and this delta y for integration delta y. Take this b common, because integration with respect to delta y, ix is equal to this b common minus h by 2, h by 2, y square delta y. Therefore, integration of this y square delta y, Ix is equal to b integration of y square is y cube by 3, and boundary conditions are minus h by 2, h by 2. Therefore, Ix is equal to b into y cube is h by 2, this h by 2 cube upon 3 minus h by 2 cube upon 3. Ix is equal to b into h cube by 2 cube is 8 upon 3 minus h cube upon 2 cube is 8 upon 3. Therefore, moment of inertia about x-axis is b into h cube by 24 minus h cube by 24. Ix is equal to b multiplied by h cube by 24 plus h cube by 24 is 2h cube by 24. 2h cube by 24. That means this moment of inertia about y-axis comes b into h cube by 24. See here, this is x-axis, this is y-axis, and this is our rectangle of height h and width b. So moment of inertia about this x-axis is b width into height cube divided by 24. Here not 24, 2 divided by 24 is 12. So here 12 term. bh cube by 12. And here iy is hb cube by 12. Similarly solve like this iy is hb cube by 12. Now which moment of inertia is bigger? See, for that calculation consider this 3-meter distance, width is 3 meter and height is 2 meter. Therefore Ix is equal to b into h cube. B is 3 into h is 2 divided by 12. That means 2 unit of moment of inertia is meter raised to 4. Here meter raised to 4. And moment of inertia about y-axis is h into b cube by 12. H is 2 and b is 3 cube by 12. That means 4.5 meter raised to 4. See, about this y-axis moment of inertia is big value 4.5 meter square, and about this x-axis moment of inertia is small value. That's why in our beams we provide depth more. Consider, see this same diagram like this way. This is y, rotate this diagram, and this is x, and this is h. This diagram rotate like this, and this is b. Moment of inertia about this y-axis is greater. That's why we provide depth is bigger in our RCC beams. Generally our RCC beam is, this is 230 mm and this side is 450 mm. Due to this depth we provide more, resistance to bending is more. That's why moment of inertia about y-axis is more. Thank you very much.